In the previous video, we're able to establish the continuity of sine x using the definition of the continuity at a point C. This time, we are going to proceed with the continuity of the cosine function, or f of x is equal to cosine x on the set of real numbers as well. So same thing as last time, in the previous video for sine. Take note, this is an example of a trigonometric function. Hence, we may need here important trigonometric identities in order for us to structure the proof of the using a definition. The definition, snippets of that, only in the part of the definition I would like to write here that will be used on this proof. Of course, the definition for continuity at the point C is this: let A be a subset of R, let function f is the mapping from A to the real numbers, and C being an element of A. Okay, then A is again subset of R. Then we can say that f is continuous at the point C if, here it comes, if for every epsilon greater than 0 there exists delta greater than 0, such that if x is any point on A satisfying this inequality, the distance of x and C, where C is an element of A, is less than delta, then we need to show that the f of x minus f of C is less than epsilon. We need to target this as part of our goal. And take note, we already have our f of x. For our f of C, where C is not defined as long as it's part of the real number, you have here cosine of C. Before we could start with our proof, take note, as part of the criteria, there exists delta. So we need to show the value of the delta. And we can do that by doing a certain scratch work. This scratch work here will allow us to work backwards, starting with our target until the intended expression that would contain this. Take note, our goal is x minus c, because this is related to delta, and what we were trying to represent is the delta. So once we could come up with x minus c, it's easier for us to define what delta is. So let's work on this. F of x is actually cosine x minus cosine c, still less than epsilon. But again, this is a trigonometric function, so we cannot simply say x minus c is something like that. Hence, we'll be using here trigonometric identities. Let me separate this here. We're going to return to this later, as well as that formula. But we would like to present here an equivalent trigonometric identity if we have cosine x minus cosine c. Let me use c because it's already here. Okay, this is just equal to this expression twice. Sorry, if it's cosine, my bad. Okay, you will have here negative twice. You will have here sine of your angle 1/2, the sum of x and c, and then we have here sine times 1/2. I am sine of 1/2 times x minus c. This is the idea, or the, what do you call this one, the identity for cosine x minus cosine c. Take note, x minus c is here. Again, that's our goal. So basically, we have that. Aside from this, before we can substitute that here, there are also important concepts that need to be discussed here, because we will have sine and absolute value later on. No longer cosine, because once we substitute that, cosine will not longer be around. But this is very important. When you say the absolute value of a certain sine z, where z is any angle, there are two possibilities. The first one is less than or equal to 1. This is true when you imagine the unit circle, always less than or equal to 1. This is true for all. But another situation is expressed in this, that is less than or equal to the absolute value of z. Now, this is not true for all, but only for small values of z. Okay, but since we are going to deal with absolute value of sine angle later on, let's introduce these two, where this is more acceptable than this, but these two are actually true for a smaller value of z. My point here is this one. Once we substitute this equivalence here, and our target again is the absolute value of x minus c, where this will appear later on, this is what will happen next. Okay, let me go back to the intended plan. Okay, you have here the absolute value of cosine x minus cosine c is less than epsilon. So we'll return to that later. Okay, this is just equal to, again, this trigonometric identity. Negative absolute value of negative 2, you have here sine, the angle is 1/2, and the sum of x plus c. And then you have here another sine, and the angle is 1/2, and x minus c. They are all under absolute value notation. We have three terms here. We can always separate them into separate absolute value notations per property of absolute value. So they have the absolute value of negative 2, the absolute value of sine, 1/2 of x plus c, and then we have also absolute value of sine, and then 1/2 of x minus c. Okay, hopefully you're following. This is actually 2, right? The absolute value of negative 2 is 2. Well, how about this 2 here? Take note, we have already established this. The sine of an angle, okay, is greater than or equal to 1, or greater than or equal to the absolute value of z. But which of these two? Because we have both signs here. Which of the two will be included? Now take note, our goal is x minus c. In short, x plus c, it's okay for that to be removed, so no need for z to appear. Here we'll be applying 1. But once you apply that, we will no longer use equality here, even if for the absolute value of negative 2 is 2. It's because it's the entire expression. This is less than or equal to 2, and then this here will be using the 1. 1 will appear, so that x plus c will not reappear here. But as for this, you have the absolute value of sine of 1/2 times x minus c, and x minus c is here. We would like to use this second so that it will be the angle itself. So the absolute value of the angle, 1/2 x minus c. Okay? So once we have that, of course, we can take this out. Less than or equal to 2 times 1/2, and absolute value of x minus c, and yay, we have isolated x minus c here. Hey, I said yay because it's finally there. Once you combine this, this is just equal to absolute value of x minus c. And finally, the exact form of x minus c has appeared. And what is this, by the way? This is all less than epsilon, so this is also less than epsilon. Now, all of this scratch work is intended to identify the correct delta to exist. And since the absolute value of x minus c, or x, yes, is less than delta, and the same is less than epsilon, one can conclude that delta could be assumed to be equal to epsilon because they are of the same value here. Okay? Now, since epsilon will exist as we declare it later, delta will also exist, and we are done with this part. We can proceed to this, and finally, hopefully achieve this form. This is the proof. Yes, this is the proof time. Let epsilon be greater than 0, and we have to assume that delta is equal to epsilon. Since we have declared that, then we can proceed now to the inequality. If x, absolute value of x minus c, is less than epsilon, or x minus c, epsilon or delta, then we have this goal. Hopefully, we can simplify it. The absolute value of f of x minus f of c is equal to the absolute value of cosine x minus cosine c. And the other purpose of this scratch work is we can pick something here that is already a simplified form of this. And why not use the last portion because it's already simplified as x minus c. But take note, this is less than or equal. Okay? You will have here less than or equal to the absolute value of x minus c, which is less than our epsilon. When you look at this one, this and this portion comprises our target. So we have finished our proof. Hence, the absolute value of f of x minus f of c is less than epsilon. And then we can have our concluding statement. Since epsilon greater than 0 is arbitrary, then we conclude that, say your conclusion, the cosine function, or f of x being cosine x, is continuous on the set of real numbers. And this is it, the final part of our proof. The proof is shorter, but it could have been longer if we don't have scratch work. So that's why we are doing scratch work. We have a lot of purpose, determination of delta, guide on the final output, the guide of expressions to be used, and so on and so forth. Thank you very much for watching.